It's Professor Dave. Let's define the derivative.
He knows a lot about all kinds of stuff. Professor Dave explains.
From our earlier investigations with slopes of tangent lines and instantaneous velocities of falling objects, we gained a basic grasp of the concept of differentiation. So let's move forward and expand upon our understanding of this operation. When we first introduced differentiation, we looked at a method for calculating the slope of a tangent line. By using this method of exhaustion, we were performing differentiation, and in doing so, we found the derivative of this function at this point. This derivative was defined to be the slope of the tangent line at this point, and the slope of the line was derived from the function. The derivative of a function tells us about the rate of change in that function at a particular input value. If a function is increasing at a particular point, its derivative is positive at that point, which is just a fancy way of saying that the slope of its tangent line is positive at that point. If a function is decreasing at a particular point, its derivative is negative at that point, and the slope of its tangent line will be negative. Let's take a moment to note something here. It is crucial that we mentally separate the value of a function at some point from the change in that function at that point. If examining position and speed, we could be located at the origin, meaning our position is 0, but with non-zero speed, meaning we aren't standing there, but just passing by. Or we could be at some other non-zero location, but standing still with 0 speed. We can also think of stock prices. These can be high or low, but their values are typically unrelated to their rate of change. They could continue to climb or plummet at any moment. Now, looking at the tangent line again, let's formalize this a little bit more. Remember that our method involved choosing a second point on the curve. We can give the first point the coordinates a, f of a, and the second point can be x, f of x. As we said, the slope of this line, which we can call the secant line, is rise over run, so f of x minus f of a over x minus a. Then we can allow point x to approach point a, and we said that the slope of the tangent line will be the slope of this secant line in the limit of x approaching a. We can express this another way, with the second point in terms of the first, by saying that x is equal to a plus some other quantity, h. So h is the distance in the x direction from the first point to the next. That means this second point has the x-coordinate a plus h, and the y-coordinate f of a plus h. Now to get rise over run, we find f of a plus h minus f of a over h. This time, the slope of the tangent line is the limit of this expression as h approaches 0, meaning the distance between the 2 points becomes 0, and the points become 1. What we must understand is that we can just as easily refer to this value as the slope not just of the tangent line, but the slope of the curve itself at this precise point. If we were to zoom into the curve at this point, closer and closer, it would eventually resemble a line with this slope. And in fact, combining this knowledge with this expression will give us a better understanding of the definition of a derivative. The derivative of some function f at some input value a, which we can represent as f prime of a, is precisely this expression we just described. So to put it in words, the derivative of a function at some input is equal to the slope of the tangent line at that point. Identically, the derivative of a function at some input is equal to the rate of change of the function at that point. These are two ways of saying precisely the same thing, and that thing is the derivative of the function. Let's use this expression to take the derivative of some different functions. Let's start with something easy. How about some constant function like f of x equals 5? If we take the derivative of this, when we go to plug in values for f of x plus h and f of x, these will both be 5, because no matter what point on the function we are talking about, it's equal to 5. 5 minus 5 is 0, so as h approaches 0, f prime of x will become 0. This makes sense, as the rate of change anywhere on this function is 0, because the value of the function never changes. So let's make a note that when we take the derivative of a constant, any constant, it will always be 0. This should be reassuring, as it means that our precise math is aligning with the intuitive idea we wanted it to reflect. Now let's try the function f of x equals x. If we try to find the derivative of this, for f of x plus h, we get x plus h, and for f of x, we get x. So x plus h minus x means the x's cancel, which gives us h, and h over h is 1. So the derivative of x is 1. Now let's try x squared. Up top, remember that we are plugging x plus h into the function first. So we have x plus h quantity squared minus the function itself, or x squared. Now we have to FOIL this first term on the top, and we get x squared plus 2xh plus h squared minus the x squared, and that leaves us with 2xh plus h squared. Dividing both terms on top by the h on the bottom, we get 2x plus h, and when h goes to 0, that leaves us with 2x. So the derivative of x squared is 2x. Let's do one more, x cubed. Now we have x plus h quantity cubed minus x cubed. We should know how to cube this binomial by FOILing two of them and then multiplying the result across the third binomial. But for the sake of time, let's just show that this will be x cubed plus 3x squared h plus 3xh squared plus h cubed. We subtract x cubed and we get this. Dividing through by the h on the bottom, we get 3x squared plus 3xh plus h squared. As h approaches 0, we are left with 3x squared, so the derivative of x cubed is 3x squared. By now we might be able to recognize a pattern. It seems that every time we take a derivative, we are taking the exponent and bringing it down in front to become a coefficient, and then reducing the exponent by 1. This is called the power rule, and it works for any function where the exponent n is a positive integer. In this way, the derivative of x to the n is equal to n times x to the n minus 1. The power rule is something that we will be using day in and day out in order to take the derivative of various functions. So the good news is that we don't have to keep using the other more tedious expression. But hopefully in deriving this new one, we have developed an even better understanding of what it means to take the derivative of a function. Just as before, it does mean to find the slope of the tangent line at a particular point. But with this new power rule in our pockets, we can now safely learn how to find derivatives without having to draw graphs or think about tangent lines at all. Instead, we can simply apply the power rule, as long as we make sure to remember what's really going on under the hood of this fancy machinery. So let's move forward and get some practice with the power rule. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.